Hello, good morning, everyone. We are waiting 1 minute to ensure that everyone can join. Okay, I think the room is getting full. So good morning and welcome everyone at our webinar, Advancing Open Science, Interoperable Data Access and Cloud-Based Workflows. We are delighted to have you with us today for this joint training event hosted by FERIS and Blue Cloud 2026 project. My name is Gabriela Rogowska from Trust IT Services, communication partner for FERIS. And I'm joined by my colleague Rita Meneses, communication partner for Blue Cloud, along with an excellent lineup of experts from both projects. For FERIS, this marks our final webinar as the project approaches its conclusion. However, we are very pleased that Blue Cloud 2026 will continue building on and ensuring the sustainability of many FERIS results. And we warmly invite you to visit the FERIS website and see our results, explore the outcomes of the project, and stay engaged through Blue Cloud. And before we begin, just a few housekeeping rules. So please keep your microphone muted and camera off, unless invited to speak by hosts. The webinar is being recorded, so please anonymize your name if you don't want to that it appears on the recording. And both the slides and recording will be available on the page of the event page, both on Blue Cloud and FERIS websites, hopefully tomorrow. We invite you to introduce yourself in the chat by saying hello and letting us know where you're from. And please use the Q&A box for the questions. There will be a Q&A session at the end of the webinar. And finally, feel free to share your impressions on social media and stay engaged with us on those channels. So let me briefly walk you through today's agenda. If we can. Okay. We will begin with opening by Erwan Boller from Ifremer and Massimiliano Assente from CNR, Italy. And this will be followed by the session on data discovery, data access and data analysis. And a joint coastal water dynamics pilot from FERIS and Blue Cloud 2026. And we will close, as I said, with a Q&A session and final remarks. So with that, it's my pleasure to hand over to Erwan and Massimiliano. I think Massimiliano is first from Blue Cloud. Thank you.
Good morning, everyone. Thank you again for attending this webinar. So just a few slides to introduce both projects. So I will start by introducing Blue Cloud 2026, which is I see funded project that is started in January 2023. And currently, as Gabriela explained it already, we are approaching, let's say, we are in the final year of Blue Cloud. So Blue Cloud is about a federated European fair and open research ecosystem for oceans, seas, coastal and inland waters. And when it started, it built upon its pilot, let's say, Blue Cloud project, which established a cyber platform providing researchers access to multidisciplinary dataset from observations, analytical services, and computing facilities essential for Blue Science. During this year, we aimed at further evolution of this ecosystem into a federated European ecosystem to deliver fair and open data analytical services instrumental for deepening research of oceans, coastal and inland waters. One of the say key feature of Blue Cloud is that it supports the EC mission Restore Our Ocean and Waters with its work program and the development of the European Digital Twin of Ocean, the European DTO, which aims to model oceans' multiple components, providing knowledge and understanding of the past, present, and create trustable prediction of its future behavior. In 2025, Blue Cloud was selected among other, let's say, 13 nodes. It was selected to be the EOSC node for the thematic marine node. So the EOSC marine node for European Open Science Cloud, and to serve the needs of the EU blue economy, marine environment, and marine knowledge agendas. Next slide, please. So the Blue Cloud Consortium is I say a solid consortium formed of about nearly 40 partners, and in this it is a very nice, let's say, mix of partners. It contains, let's say, is comprised by, of course, excellent scientific partners, but also technological partners, data infrastructure partners providing the marine data, so a number of what we call Blue Cloud data infrastructures. And of course, in the consortium, we also have partners that deals with the communication, exploitation, and sustainability of the project. Next slide, please. Right. What are the main outcomes of Blue Cloud? So there are, let's say, four main services. One service is the data discovery and access service, which provide access to more than 10 million open datasets and produced by the three major Blue Cloud data infrastructure that we have in the project. And then we have in open science virtual research environment, federating multiple infrastructures and supporting analytical big data workbenches and virtual labs that is based only for science technology. And we have a number of essential ocean variables, what we call workbenches, that work on, let's say, discovering and providing highly qualified data collections. And then over this, we have a number of virtual laboratories. We have 5 domain-based virtual laboratories that deals with a number of let's say, use cases, starting from coastal ocean observations to global fishery atlas. Next slide. Sorry. Back, sorry. Yeah. Since we are in the last year of the project, all the services and products that we have been working on are available in the virtual research environments, and also the virtual labs are available for you to try. So just go to blue-cloud.d4science.org. You can register for free and you can access the 5 domain-based virtual labs if you wish. Next slide, please. And this is my last slide, just to give you a hint on the virtual lab data types that they are working on. If you can see on the top of the slide, you see the blue data infrastructure, so the data providers that are in the Blue Cloud Federation, and the virtual labs on the bottom, and the kind of data types they are dealing with to let's say provide the scientific excellence and use cases. And this is all for Blue Cloud. Thank you.
On my side, so I will present briefly the first project. So, the first project funded by the EU and under the Horizon Europe aims to make environmental and earth science data more findable, accessible, interoperable, and reusable. So in practice, we develop services that simplify the discovery, access, and analysis of multidisciplinary data. So from, for example, satellite observation to in situ measurement. The project started in September 2022 and is coordinated by CNRS with a consortium around 20 European partners. The project ends this week, so it's the end. And the ambition of FAIRIES was to integrate these services into the Europe to the EOSC, supporting more open and collaborative science. So, to ensure that the FAIRIES services really meet researchers' needs, the project is and the services has been tested through 5 pilots, and together these pilots demonstrate how FAIRIES can support very diverse scientific domains while using the same services. So the main outcomes of FAIRIES, or this is the big picture of the FAIRIES project. So we relied on 3 cross-cutting pillars, so standard and interoperability, end-to-end fair principles, and interdisciplinary in collaboration. And one of the challenge of FAIRIES was to reuse existing technical solution, and extend them to other domains. So we worked on improving the diving into the data, so with discovery, access, and analysis. For the data discovery part, we work on an IDDAS, so we added the I before DDAS used by Blue Cloud, for example. It's for this means interdisciplinary data discovery and access services. We also work on data access on the server side in order to improve the access to a subset of data, but also from the client side in order to maybe hide the complexity and the kind of jungle of these heterogeneous services that can exist. We also work on data analysis with interactive application, and with different kind of tools to use interactive notebooks, workflows, for example, with Galaxy, but also visualization with ODV. And we added a lot of thematic tools in these services. And the last point was to provide integrated infrastructures that we call EAL for Earth Analytic Labs. So we provided 3 different EAL that we interconnected through federating capabilities such as SSO and EAM using the AGI checking, and also providing the same user space via an S3 bucket stored hosted at UCA. And we also, as I mentioned previously, work with real-life use case, so with the 5 pilots, but also we organized a 3-day hackathon in March, and for this hackathon, we we use and we provided a new demonstrator on the Unga Tunga eruption that allows to really work on interdisciplinarity and of course on collaborative science. I think that's all for the ferries part, and we signed an MOU in November 2025 between ferries and Blue Cloud. That's why we have this webinar today. So I think we can go to the next presentations. So we will start with data discovery with Jack, I think.
Yes, everyone, thanks. Let me take over. Right. Okay, great. So hello, everyone. Nice to see you all here. So today I will be talking about the data discovery and access service by Blue Cloud, but also the interdisciplinary data discovery and access service developed by Fair East. And then Alexandra will take over and dive more into the Fair East DCAT metadata profile. So before I dive into the Blue Cloud version, I wanted to highlight really the differences between the two. So in the Blue Cloud project, we have a set of Blue data infrastructures that are behind the data discovery and access service that are actually part of the project, which means that we have time and effort available with the partners to focus on harmonizing and expanding the web services that they offer. So a lot of work has been put into this action over the last years, while also promoting the uptake of controlled vocabularies by well-known vocabularies in the marine domain to really upgrade the metadata and related semantics. All with the goal to really optimize the fairness and the content of the BDIs. So this discovery service really serves as an, let's say, a checkup and a validation of what the efforts have, well, resulted in, and also as an internal gateway for Blue Cloud for the users in the virtual research environment that Massimiliano has shared before, to gain access to the data in an easy manner to work on their services. Well, then if we look at Fair East, we actually are looking broader than just the marine domain. So we're also venturing into other domains, and we have, well, the data infrastructures not being part of the project, which means that we have to deal with what is received from them as is. We don't have efforts to work on harmonizing and standardizing the way they expose their data and metadata. So we decide to come up with a bottom-up approach where we defined a metadata model, common metadata model named DCAT Fair East, and Alexandra will dive more into this detail to provide as a kind of a standard layer on top of all these various different metadata standards that are in use by these different domains, and trying to build a layer on top of this for users to easily search through the different assets. And then finally, we also try to include semantic brokerage and map different raw labels to URIs from well-known vocabularies in order to improve the metadata. So that's where the distinctions come in with these two approaches. And we also linked the Blue Cloud Access Service to the Fair East one, which I will share a bit more into detail. So yeah, for the Blue Cloud one, I will skip most of the introduction because Ms. Juliano has already shared a bit on that. But yeah, we have the pilot started in 2019 and was extended in Blue Cloud 2026 until next year. With the main goal to really deliver this powerful virtual research environment where we have VLabs, workbenches that can work on their services. And with this discovery and access service, being able to feed them with the data from the Blue data infrastructures in an easy manner. And this is, I think, a great picture that shows all the components of Blue Cloud. We have the virtual research environment at the core, and then on the left we have this discovery and access service with all the blue data infrastructures that we see there. So users in the VRE are able to pull data from these infrastructures that they will then use in their services. And then we also included data lake technology, such as Beacon, which I will explain a bit more in a later presentation today, that then feeds these workbenches that try to create data collections based on different essential ocean variables for the physical domain, the chemistry and the ecosystems. And they really require subsets of all these data files that we obtain with the Discovery and Access service. So a lot of effort was put into that. But before we could do that, all the work that we did previously in updating and improving the web services and the way they expose their metadata has really helped in how complete the metadata is and how well the researchers can work with it. And then also we see the V-Labs that Massimiliano has mentioned before that work on different topics, produce services that anyone accessing the VRE are able to use, which is really nice. And then I also have a link to Edito, so that's something that's being discussed at the moment. So work is ongoing to have a link in the future with Edito. And the idea is that Blue Cloud, as the EOS Blue node, would become a third component of Edito, and really focusing on being an incubator with more mature applications that could then feed into Edito or the underlying components like EMOBNet and Copernicus Marine. On the left, shortly recap on the blue data infrastructures that we have in the Discoveries and Access service. And then also we have the infrastructures that are really supporting the virtual research environment. And this, I already mentioned part of this before, but really the main concept and idea of the Discovery and Access service was to really validate the content that we receive from the blue data infrastructures and feed as a data gateway to the virtual research environment. So all this work that was put into these web servers and APIs, and also the promotion of controlled vocabularies was, I think, very, very useful. And the work is not done yet, so we will continue to improve this and try to optimize the fairness and the contents of the PDIs. So this is how the service looks from the user interface. So we see here the blue data infrastructures, and we see two different levels. So we have two levels where you can identify the data. So it's at more data collection, so more higher level. And then secondly, we also have the deeper, more detailed granules. So really the individual data files that you're able to request and pull to the virtual research environment. So now switching to VREs, where we are venturing more outside of the marine domain and also looking at other domains. So we're really looking at use cases that focus on, for example, the ocean, but also atmosphere, and that require data from different domains. So this was the challenge in VREs that we tried to solve. And immediately it was clear that because we do not have these data infrastructures as part of the project, we needed to come up with a clever approach to deal with it. So we tried to develop this interdisciplinary data discovery and access service to create a harmonized layer on top of all these files that users are able to search through and access the data. So we developed this DCAT profile that Alexandra will dive into, and we created metadata completeness reports. So for each of the providers, we tried to see and score for the elements in their metadata, how well filled they are, so how complete is the metadata that they provide, what kind of elements that are usually required are missing, etc., and then feed that back to the provider. And we created a tool called the Semantic Analyzer, and I think Alexander will shortly touch upon that too, that extracts semantic content. So these are raw labels that are not connected to a vocabulary, but with the help of the tool, it will map to a knowledge base of existing vocabs to find and map URIs to these raw labels in order to improve the metadata. So this is kind of the architecture of the ideas, where on the left side we have the user looking at the user interface, a Sparkle interface, and on the right side we have the data infrastructure. So we have a link here to Blue Cloud, Blue Cloud already put all this effort in harmonizing and expanding the web services. So we just try to build on top of that and gain access to the data from the Blue Cloud BDIs. And then in this project, we also have a whole bunch of data infrastructures that are from other domains, for example, Copernicus Land, Atmosphere, etc., that we harvested with the GeoDAP broker. And then all the metadata standards on the right are converted in the end to the RDF data profile, which we use to build a interface on top of it. So that's what we see here. We have 3 services that are running for the IDDOS. We have the Sparkle interface that allows you to search machine to machine through the assets that are provided by the data infrastructures. We have the user interface where you're able to go through the data infrastructures and download the different files. And then finally, work was also ongoing in trying to look from a virtual research environment perspective and see if we could pull in the data from there. Well, so the URL is on the screen. You're able to do free text search, look at a map and select the bounding box, select parameters, the catalog that you want to filter on. But important to mention again here is really the results. So that you see when you start searching depends on how complete the metadata is. We could not change that, but we all fit it in our DCAT profile, so at least we have a harmonized metadata profile to look at, but sometimes the fields could be missing, and that's just up to the provider to improve. And the user interface and Sparkle that directly builds on top of the RDFs, so the DCAT, so there's no intermediate database, and that's also really well result, I think. And yeah, again, we use the semantic analyze to upgrade the metadata. I think here I will give over to Alexandra, who will talk more about the metadata profile that we developed in Phrase.
Thanks, Dirk. So I will share my screen. I hope you can see it.
Yes.
Brilliant, thank you. So
Presentation mode. Yes.
Yeah, thank you. So I will start directly with DCAT and what DCAT is. So DCAT is the data catalog vocabulary. It is encoded in RDF, which is the resource description framework. And what it does is that it enables a publisher to describe the data sets, the data services that are in a catalog and all the relationships that hold between them. All this using a common language and a standard model that facilitates the consumption and aggregation of metadata from multiple catalogs. DCAT was developed and is still maintained by W3C and is currently in version 3. A very important fact here is that DCAT is machine readable, and it is machine readable because it's written in RDF. RDF, which is the resource description framework, structures everything in triples. Triples that contain a subject, a predicate, and an object. So you can express sentences like this URL is a data set, or this URL was actually created by Woods Hole Oceanographic Institution. Most importantly, you can say these subjects, predicates, and objects using unique URLs. So a computer or a machine doesn't have to guess how to interpret an RDF document. They know it's triples. They know exactly what each one of these subject, predicates, and object is, and they know how to interpret them. So if you write lots of sentences about your data sets, you can then create a graph like that for one of your data sets. And then if you have many of them, you can actually put all of these triples in a triple store, which is what we have in Fairies. This triple store can then be queried using a language called Sparkle. If many providers put their data sets in triples and consequently in triple stores, then we have a web of triples of data sets that can be queried using federated queries, and we can all be harmonized. That's why we chose to have RDF and DCAT. So our mission for FAIRES was to be able to provide discovery and access to our scientists to data sets that were both cross-discipline, so they were including solid earth, atmosphere, and ocean, but they also were from diverse types. So they were in situ, satellite, and model data. And finally, they were coming from many different sources like the World Ocean Database, the Copernicus Marine, the Argo, the Sentinel Copernicus, and so on. So we didn't have access to those, as Jerk said in the beginning, which means that we couldn't change any of those data. So DCAT and RDF was chosen because it would make, if we harmonize those data, it would make them more fair and more discoverable and interoperable, machine readable, as we said before. DCAT is domain agnostic, so you can describe any data set. You can then federate. It is widely adopted and used, and it can be extensible. So we can start from a very small description of a data set, and we can gradually make it bigger without losing what we already have. So our scientists gave us a list of terms, a list of fields for describing the data sets that were very important to them. This helped us create an application profile for DCAT. An application profile is a way to adapt a general standard for a particular context, and in our case, adapt DCAT to FAIRES. The application profile defines which elements can be mandatory or optional, what kind of values we need for each field, and what kind of constraints we want to apply to those data. And with that, we came up with a list of many, many fields, what each field means, what can values be for that field coming from vocabularies, controlled vocabularies. And then we mapped them to a DCAT property or any other property, even if it was not part of DCAT. And with this table and many other ontologies, we managed to create an application profile for DCAT called DCAT FE, which is FAIRES. So DCAT FAIRES includes, apart from DCAT, schema.org, the data quality vocabulary, the PROV ontology, FOV, the Dublin core ontology, so properties from many other ontologies as well. And what we did is that we produced Turtle file for a full data set in DCAT FE, and the SACL file to be able to automatically validate, but also to automate our process and make sure that what we create is already DCAT approved, DCAT FE approved. And the final one, we also made sure that it aligns with GeoDCAT AP. Now, getting all of this information, so going back to the scientists that told us we want data sets that are coming from the different sources, we first needed to collect all these sources and then see how we can connect to these sources and get the data sets to harmonize them. So we then had to discover all the different endpoints these data providers have. When we discovered the endpoints, we connected a broker called GeoDAB to these endpoints, and GeoDAB has this magic ability to harmonize the outputs of these endpoints to ISO 19115 standard. And then we mapped this ISO 19115 to the Ferris DCAT. And with this mapping, we managed to create a triple generator that mapped this output to the Ferris DCAT, put everything in a triple store, harmonize them, while also giving them a semantic uplift with the semantic analyzer where possible, and put a user interface, which is the IDDAS, on top of it. And that helped us discover and harmonize datasets that were cross-discipline. And with that, we can go to the next one, which I think is still JERC. And Beacon.
I think there's another data access presentation before me.
Okay.
Okay, for the data access, it will be content.
Yeah, I show. It's okay here?
Yes, perfect.
Okay.
And maybe next slide, Quentin. Just a short introduction for this part. So we showed previously the data discovery part, and now we will present a data access part with both server side and client side part. For the server side part, we will present two different approaches. The first one with some new standards with S3, Arco, Stack, and OpenIO implemented on Examine, and the second one with Beacon, a data lake solution platform developed by Maris. And for the client side, Mark will present an innovative concept which is called UDAL for Uniform Data Access Layer. So Quentin, I leave the floor to you.
Okay, so for this first part, we'll talk about Continuum S3, Arco formats, Stack, OpenIO with Examine Community. So just a point, Examine Community is a server, a map server developed by Geomatis. So I work at Geomatis. And we also work during Ferris to implement this technology. So what are these technologies? They are at the core of modern Earth observation, data storage, and sharing systems. So it's a four pillar approach with the store pillar, which is scalable object storage accessible via HTTP. So this is the foundation that hosts your data in a durable and accessible way. So the foundation of the building is an S3 storage. Then you have discover or find pillar, which is a common language for describing and searching for geospatial data wherever it's located. So this is a world of Stack. So we'll talk about this technology after in details. You also have an access pillar. So these are 5 formats that allow direct and partial access to data stored in the cloud without unnecessary downloads. So this is the principle behind Arco formats such as COG, GeoZar, GeoParquet, and more. And you have a last pillar, which is process. So it's a standard API that for sending processing tasks to data directly where it's located, so on the server. So here is a mission for OpenIO. So what are Arco formats and S3? So S3, it's a cloud file system. So it's an object storage where you can store data and metadata at the same place. And it comes with over HTTP protocol. So it gives you fine-grained access control and HTTP range, byte range. So the goal here is to you store the data on an S3 file system, and then you can request using HTTP protocol directly your data or subpart of your data using HTTP range. You only download the part you want. And it works well with Arco formats such as ZAR, COG, or GeoParquet, for example. So Arco formats are formats where you have metadata and chunked data in your global data. So you have a file, and inside this file, you will have typed data or chunked data. And when you request this data using HTTP range in this tree, you can subset your data directly with the request. You only download the type you want, use the chunk you want. So it's easy to use. You have an example with Xarray, for example. You can request a ZAR or subpart of ZAR. And also it allows you to do some parallel or distributed processes. So the other pillar is Stack for spatial-temporal asset catalog. So it's not a format, but a metadata standard to request your metadata and the data associated with from a server. So it comes with the structures and components in JSON. So you have an item, which is metadata about a single geospatial asset. We have a collection, which is a group of related items, a catalog that organizes multiple collection and items. So you have the schema on the slide. And you can add extension to your metadata for specific use case. So EO extension for satellite data, for example. What are the benefits of Stack? So it's a uniform data discovery. So you can find assets across organization and clouds. It's widely used. So many clients use or rely on Stack. You have an extensibility with the metadata extension for new use cases, and it's adopted by major data providers such as Copernicus, NOAA, NASA, and more. So here is an example of Stack endpoint or architecture from Ephemer, and on the right you have an example of web interface with Stack metadata, and also an example of code in Python to request Stack collection from a Stack endpoint. And the last pillar is OpenEO. So what is OpenEO? It's an open standard and platform for processing and analyzing Earth observation data in the cloud. So make EO data access, processing, and analysis scalable, reproducible, and interoperable. It comes with a web API that connects Earth observation cloud backend in a simple and unified way. So it's accessible via many clients and languages. And the goal of OpenEO is to apply remote processes on data cubes and chain them in a single workflow. So you will have small blocks of process, and you can chain them in the workflow and send this workflow on the server. The process will be executed on the server side, and you only download the result. So no need to download the whole dataset or move massive dataset in the network. And OpenEO also use Stack to expose available data on the server, and it's also compatible with ARCO formats for cloud processing. Here is an example of OpenEO with Copernicus. So here it's an NDVI process with a web interface. So you can see the block of data, then the NDVI process and the result. Then you run the process and you directly get the result you want. Another example with Examine. So during the first project, we implemented an OpenEO endpoint in Examine community. So here it's without web interface, but you can also use OpenEO so with a web UI or with directly the API. So here is an example with the API. So you create an EVI process, for example, in JSON. Then you send the request to this process graph with the correct parameters, and you get the result. So what are the next steps for OpenEO? So we have a use of OpenEO in Examine community on Dataterra's, on Dataterra data hubs. So we have Tetis and Taber. We are towards a federation of OpenEO backends. So there is already a federation at Copernicus. We will also have federation within Dataterra. And OpenEO will be also in Galaxy with the web editor, result to history, and provenance. And now I will let the floor to share for Beacon.
Thanks, Quentin. Okay, so yes, I will talk a bit about Beacon today. So a bit about the history of Beacon and why we started developing this data lake software. So in the case of CDataNet, we already had millions of data files. which had access to the files, the data sets, that was possible, but actually getting slices of data over time or over a region or over depth, that proved to be difficult. So we were looking for a way to optimize the system for machine-to-machine access, to actually subsets of these large data collections, to easily work with it in a Jupyter Notebook or other applications. So how do we go from serving files to an actual data lake? So that could be an example request. I need all the temperature data in the North Sea from 10-year time period in a degree Celsius at a certain depth. And then I want to have just one netcdf file or any other format that contains just this data, which I can directly use and work with. And that just speeds up the process of working with the data dramatically. So we have been using and developing it in various European projects and now also in Fair East and Blue Cloud. So shortly about how Beacon works and what are the components. So it was written in Rust and C, runs on different operating systems. And it's very simple with the use of Docker containers for anybody to set up their own Beacon node. So if you have a data collection, you can set up your own Beacon node at your server, and enabling easy access to your collection via Python or any other service. So it consists of a set of core libraries and a REST API, and how it works is if you have a data collection somewhere, you point to that collection and it starts indexing all this information. And because it has indexed all the data, it knows where to look. So if you send a certain request to the Beacon endpoint, it does not need to go into every file to look for the data. It already knows because of the, let's say, the tags for each of the data files, making it very fast, and you're able to work with it on the fly. So you can produce a whole bunch of different output formats that have certain use cases depending on, for example, what kind of information is in your data output. If it contains more text, because you have a lot of metadata columns, you might want to opt for example, APC, so the Apache Arrow. Well, if you work with gridded data, maybe netcdf might be a better option. And you can apply different types of filters, so range filters, polygon filters, metadata filters, depending on what you're looking for. So currently we have it for anybody available on the beacon.mars.nl. We have some documentation and GitHub available. And yeah, as I said before, it's really simple to set up your own Beacon node at your server. And well, of course, we can assist if you need that. And in the context of Blue Cloud and Fair East, we have set up different nodes ourselves to well-known data infrastructures. For example, Argo, EMODnet, etc. That users are able to request in Blue Cloud in the VRE and in Fair East on the UCA testbed. So here we have some example nodes that are available that are hosted by us, but really also the goal is for Beacon to be applied to other data collections by the providers themselves. And just to share a bit how you would be able to access Beacon. So on the right, we see an example for the World Ocean Database. So what you do is you have the endpoint. In this case, we have beacons wod.mars.nl, and the only thing you need to do is to provide a query body. So this is a JSON object which contains the columns that you are looking for. So a data collection could have, for example, 100 different columns, but you might only be interested in a subset of them. So that could be the parameter, the unit, the depth, the longitude, latitude, the data set, and some metadata that you also need for your research. And then you're able to filter on these columns that you select. So in the case of, for example, we see temperature, we could well, do a certain region request or whatever you are looking for, or just focusing on the data that's produced by a certain cruise or by a certain country, etc. And recently we also added the Python library, so it's a bit easier for the user. So you're not really have to setting up you don't need to set up your query body yourself, but you can just select the columns that you want in just one single line of code, and then you will be able to access the endpoint as well. So that just makes it a bit easier. And we're also working on a user interface for the ones that are not familiar with Jupyter Notebooks, and they will be able just to select a node and then with simple user interface widgets select the data that they're looking for, plot it on the map, download it, look in the table, etc. And I just wanted to share some examples because you can also apply it to draw data files, for example, on the map. So you could make a web request to the beacon endpoint. In this case, we have the Copernicus Marine Cora time series, and you can just quickly plot the data on the map. Or if you work in a Jupyter Notebook, you can compare different data infrastructures, find outliers, and just easily do a query. Okay, I want 70 years of North Sea temperature at the top layer of the sea, and then I want to create a time series, for example. And this is a screenshot from the user interface that we're working on. So then you're just able to select, in this case, okay, I'm looking for the Argo node, plot the data on a map, and let me see what kind of data is in there. So you can click on different points and find information, so also the metadata. And important to mention here is that if you obtain data from the beacon endpoint, you will always be able to go back to the original metadata file with the identifiers that are maintained. So we're not changing any data in that sense, and you will always be able to look at the original metadata file. And we're also venturing a bit into more in other domains like climate, for example, here. This is a screenshot from the user interface where we see ERA 5, which is a commonly used data product. And you see here on the left, it looks more like an image, but actually if you zoom in, that you see on the right, there are just gridded data points that are plotted on the map. And we are also exploring this now in some national initiatives to see how we can apply it on national nodes of data in different domains. So it's not just for the marine domain, it's extendable to other domains as well. And now I give the floor to Mark.
Hello, good day. I'm trying to switch to my screen. Hope you can see it.
Yes.
I do get an echo on my side, so I'll just continue. So yeah, it's rather easy for me to conclude on this data access after these two previous stories on OpenAO and Stack and all that stuff and Beacon, because those are actually showing how on the server side, a lot of new technologies are being applied. And what we are trying to do here in this last step is making sure that all those differences and all those new developments are not hurting the client-side development too much. And for that, we introduced this UDAL ID, which is an acronym, sorry for yet another acronym, standing for Uniform Data Access Layer. Next slide. Good. Well, we start from the observation that there is today a very high impact of all these technology or data provider changes on how data visualization, VREs and workflows are using those data. So there's a bit of a claim here that's saying X, we haven't measured it, but a large amount of data access code in those data visualizations and VREs are in actually considering the aspect of how to get to the data, right? And so what you find in there is hard-coded sources, hard-coded processing, often very spaghetti-like in the case of Jupyter Notebooks. You have part of analysis stuff and then the realization, oh, I need some more data, so we just add some more very detailed stuff to get in more data and then do some more analysis. And it's hard to keep an overview of what the data is actually is about and what the research is about, what we're trying to prove here. And this is the big ambition of UDAL, is trying to enable a new way of writing your data visualization VRA and workflow more research-oriented coding to be only considering 100% what the data is about and what you are dealing with, and all the how, pushing all of that to what we call brokerage. So actually to different packages or libraries that deal with that stuff. Another way of looking at it is that actually, if you look at the complete data cycle, we see there's only one cycle. And the impact of any changes on either end is felt across the whole pipeline. So if there's new ways of doing the data publishing, or there is a new data catalog, or there is a new way, like you've seen a minute ago in Beacon, to very effectively publish through a new technology subsetting of that data and querying of that data, well, then actually everybody is just happily expecting that people will rewrite large portions of their VREs and just start over again, right? The UDAL concept wants to introduce separations between these life cycles. So making sure that there is, and a typical system engineering way of doing that is by introducing what we call contracts. So introducing a data provider contract that allows to have a separate data measurement lifecycle, where people can just change the way they retrieve their data. As long as they publish it according to this contract, everything should be fine. And I think this relates to what Alexandra was showing earlier when she was mentioning the Descartes Ferries way of publishing inside Ferries your data. On the other hand, what UDAL tries to do is then create a new contract that allows for querying, or I should say actually asking from the client for that data to be there. And this allows the new contracts allow then, well, the second one creates this analysis and reporting lifecycle that should live on its own, but in between those, we now create this new space where all this data engineering can happen, where actually new technologies should and will replace each other, maybe in a fast way, but allowed to do that without impacting how data should be provided or needing to write your analysis code. So that's the big idea. We do this through abstraction. We start from the central idea that all data access is actually similar on the outside. You select something identifiable, so you give it a name. Maybe you need to put in some parameters, but you want to get out a data frame or a data cube, and then that's the start of your research, actual VRE work or hypothesis analysis, whatever, etc. But all of that could be very different on the inside, depending on where these data sources are coming from, etc., etc. And all of that we want to hide from you. We want to push into what we call brokerage. We are honest in the sense that not a lot of these technology providers like OpenAO or Beacon, of course, UDAL is a very new idea, so they're not concerned with adapting to this UDAL. So today you probably would need to write your broker yourself, but at least this broker allows for this required isolation. And it's really just a systems engineering technique where I was mentioning earlier the introduction of data contracts or interfaces or standards, if you like. There's also a link here to sustainability. What we think we are doing is we're through this separation, and I think I mentioned this earlier, we can focus on stable and long-term research. So reuse your VREs, also have a reuse of historic and well-established data provider stuff. Keep all that in place, but allow for this intermediate area with a fast pacing change, with a high level of competition, where new ideas, maybe even artificial intelligence, whatever you like, you can throw in and allow for a technology change that will not affect your sustainability of your overall research. That's the big idea. We think the input-output should be decoupled more and better. I think I explained that earlier. Another interesting idea is that's the last bullet. It also matches another idea that has been emerging, which is the one of edge computing. The fact that people start realizing that the client side actually exists. And I don't know about you, but this little device has quite some, even that little device, I should say, has quite some processing power on board and computing power on board. And those clients are very close. That's why they called the edge. They are very close to the end user. So that you can tune them to answer specific, add specific computing tuned for a very limited, even a target audience of one. If this device is only used by me, right? But that's the whole idea. And the sustainability part here is that we don't try to have server-side computing power being consumed for only one user, right? So use that CPU that is close to that user, that is powered by that user for its use, rather than try and do everything for everybody on the server side. Good. That kind of then leads us to how are we going to design this stuff, and we came up with this. It's a bit weird, it's paradoxical, but the realization was that the UDAL is a thing we need, but it actually should be something that does itself as little as possible. So it's not about what typically server-side software stuff is doing is serving, right? Is providing a lot of answers for a lot of people. This is more about, no, what we want to introduce with UDAL is actually very standard and repeatable, recurring dialogue for asking for your data, and imposing it in a very consistent way in the design of your clients allows you, well, requires you to push the details into a different library, which is behind the dialogue. But this little thingy, the fact that you're separating this allows for a new piece of client-side software that either can be reused by a lot of people, but almost more importantly, that can be replaced very quickly by something else to test if a new technology or a new data provider can deliver the same kind of data and still feed your complete VRE, your analysis, your hypothesis checking, etc., etc., etc. Right? So that's the big idea behind it. It's a little bit theoretical, but software engineers, especially system engineers, think like this all the time. So in the end, what we end up is we believe there's hopefully going to be a component registry where people are indeed publishing and sharing their data access brokers, the ways to use existing technologies like Beacon or OpenAO or whatever, and have them conform to this new dialogue of providing data on the client side, right? So all these UDAL brokers could exist and live in a component registry. But also on the other side, we think we can introduce a registry of what we call the data demand, where very formal names can be introduced to describe data. Well, we've called them named queries, but query is a bit of a bad word. It's actually a data request or a virtual data set that is being named, where you know, hey, this is what I'm asking for. It could be like CO2 measurements in the North Sea with these kind of parameters, etc., etc. And I don't really care through which technology or actually even who is providing this data, as long as it's conforming to this standard. We still use the word query and not really virtual data set, because it has this element of being able to be filtered. So you can pass in parameters. So you can tune your question a little bit, only the kind of the resulting data set, the shape of that data set, that data frame, that's what's captured, and the meaning of what you're requesting, that's captured in that name. Good. What we have created is a specification, which is at this stage actually a Python library with a number of classes that, like I'm saying, do nothing. They only specify how to enter into this dialogue. They also specify how people that are creating a broker should be restructuring their code so they can fit this model. And it's really, there is one class, UDAL, where you can ask for all the available names of the available named queries. You can actually get those queries and execute them by passing that name of that query together with the required or optional parameters in a dictionary. When you have access to a query, you can also get some metadata about it, and the same holds for the query results that comes out of it. It has a dictionary with metadata on the details of the query, but also, of course, the data itself, which is just returned in any type you'd like. So you can specify the type in which you want to return your data. Up to now, we've mainly been using Pandas data frames. Good, so this is how it's then written in code. You create some configuration objects. You have selected, which is a little bit a detail, but on the first line, actually an important decision there as well. You import a certain implementation of UDAL, and then there you do a connect to a certain provider that helps you decide where to get the data, etc., etc. And then here you have, in this stage, you see the usage of the named query. So we're using here URNs, a standard technique, and a parameter set, which is just a list of languages you like to. And then here the type, like I was saying, you can specify the type of result you like. In this case, we are asking for data frames. And that's the big idea. The big idea is not the magic, oh, whoa, you did everything? No, we did nothing. We created this dialogue, and we suggest that from now on, everybody is following the same dialogue to request its data, and just have a broker implementation on the side that deals with all the details, so you can replace and easily get rid of it and use another one. Hopefully, of course, people like Beacon, OpenAO, etc., when they create new services, new technological innovations, and they want to kind of motivate you into using their new stuff, I would recommend them to create also a broker for it. So on your side, you just would need to change this first import line, use their broker implementation, and all the rest of your code should be able to just run. That's the dream. Good. So if you want to start to UDAL, what is the process? Select a specific case of how to access data. Make sure you understand and you can explain to the outside world what is going on. So focus on this what side, describe the data need, consider if you would need to do some local client-side subsetting. So if you need any parameters that need to go in there, you give it a name. Typically we assign a URI, or in our case it was a URN, but same difference. And then just rewrite your client by using UDAL. So you apply the UDAL dialog, you basically reorganize your code. If needed, you create your own broker. And if you want to share it, of course, you use GitHub and just share it. So that's me on UDAL. This is where you can find more on it. We have the lab site of Ferries at labferries.eu. There is a subsection /UDAL. The GitHub Python UDAL interface is mentioned also. And of course, we had a number of reports and documents, architecture documents, design documents that also cover UDAL, which you can find on the Ferries community at Zenodo at this link. So this is me. I'm going to stop the share.
Thank you, Mark. We can't hear you, Mari.
Yeah, You can hear me now?
Yes, all good, thanks.
I can start the sharing. Okay, so you can see the screen.
Yes.
Okay, perfect. So hi everyone. So I'm here to speak about Galaxy for Earth System Sciences. So this was a project that we led during the FERIS project, and we wanted to develop Galaxy. So Galaxy is a community-driven platform popular in multiple domains, and we wanted to expand it within FERIS for the Earth System domain. It was created about 20 years ago for bioinformatics first, but since then it largely expanded to other domains like climate, ecology, and so on. So Galaxy is fair by design. It's an open source web platform for sharing and processing research data. It's accessible, reproducible, and enables reproducible analysis, transparency, and also community work. So this platform is here to help researchers to analyze their data and be able to have big processing treatment to work easier. Indeed, it's an ecosystem of systems, and it can bring together the best of three worlds. So high performance computing for heavy tasks, command line tools but with a simple interface, and interactive environments where you have full freedom to explore your data. So the key idea is that you don't need to be an IT specialist to analyze complex data within Galaxy. This is how it looks like. So if you go onto the earth-system.usegalaxy.eu interface, you'll see these three main panels. So let's begin by the blue panel. So the blue panel is all the different tools that are available for Earth system data analysis. You can directly search by the tools by keywords here, or you can browse by section here. Then you have on the green panel the history. So the history is one of the most important parts of Galaxy. This is where you can be able to find the data you uploaded to Galaxy, but also the different steps of your analysis. So that way you can trace back everything that you did. And from this history, you can extract workflows. So once you extracted a workflow, you can have your full process and you can run it again, share it to the world. And so anybody can reuse it as they want for their own data, or even improve it with their own tools and for their own analysis. And on the middle panel, in the orange panel, you can have the tools interface. So this is where you'll be able to fill in the different parameters of the tools. For instance, the data you want to analyze. If it's data on ocean, you can specify latitudes, longitudes, and so on. It really depends on the tools and the data you want to analyze. And it's also here that you'll be able to visualize the different outputs of your treatment. So for instance, if you have an image or a graph or anything, you'll be able to see it directly in here. And finally, you can also see here on the top panel that you have multiple buttons. So for instance, you have workflow button. You'll be able to see the different public workflows that you can use, but also your own workflow that you can then improve or share. And also you have the little hat here. So this little hat here is the Galaxy Training Network. So this is basically the Bible of Galaxy. You'll be able to find all the different information that you need to really dive into the Galaxy. You have tutorials, classes and courses, pathways, and so on. So it's a really easy way to learn Galaxy and improve your skills on various domains. For instance, there is a set of tutorials on how to manage data in a fair way. So yeah, we also have a specific section for the ocean. So for instance, you can see here we have multiple tutorials dedicated on the ocean domain. So I can directly show you the interface here. So this is the Galaxy Training Network, and you can see here we have a little tag named ocean. So you can directly browse here and search with the ocean tag. And then we'll give you all the different tutorials that are specific to this topic. So you can see we have multiple of them. And I can maybe show you this example. So this is a tutorial from one of the Ferris pilot, coastal water dynamics. And you can see we have different metadata here, and then you can directly follow the tutorials and see the different steps that you need to have to do to manage your data and process your ocean data. So here in the metadata, you can see you have the workflow button. If I click on it, you can directly go here and you'll have access to the graphic interface of what the workflow looks like. You can see that we have, for instance, the input data set in the top, and then the different tools that are used and the different options that you can choose. Here on the left, you have the different metadata, and for instance, you can see that it's also published on Workflow Hub, and you can also directly download a work rate from this workflow. And here you have the different information on which kind of data you have, either the uploaded one or the directly produced one, the different outputs, and some information on which tools are used within this workflow. So this is how it looks like. Feel free to go browse yourself and play around with these different trainings. We go back on the presentation. So then I can maybe explain a bit more what is a tool in Galaxy. So as I told you, Galaxy is an open source platform for everyone, and it has multiple kind of tools for multiple kind of data sets. And these tools can be chained into different workflows, like I showed you just before. So we have different kind of tools within Galaxy. For instance, we have the batch tools. So these are tools where you can directly input parameters into a formula, and then you directly execute the tool without having to know anything about informatics. So the idea of these tools and the idea of workflows within Galaxy is that this way you can divide huge scripts into multiple small scripts that we will then call tools. So these scripts can be Python or Java. It's totally informatic language agnostic. And then once you have your different itemized bricks, you can generalize them so that they can become Galaxy tools, and then they are reviewed by the community of Galaxy, which is a really dynamic community, before being deployed in the instance on Galaxy. So as you can see here, we have an example of a workflow. So you have on the first step, the input data set, then a first tool, second one, and so on. So that way anyone can take this workflow, adapt it, so can maybe add a tool, change the input data set, do another more complex analysis with more tools, and so on. So this really enables transparency and reproducibility of your analysis. So you can see here on the top, you have different buttons, and for instance, you can also export it. So that's where you can export in workrate, for instance. And you can also share it with different users of Galaxy or outside of Galaxy. So here, a small focus, you can see we are using ODV. So ODV is Ocean Data View. And this is a particular kind of tools within Galaxy. We call it an interactive tool. So ODV is a desktop tool in Galaxy. So basically it does as a desktop application that you can have on a computer locally, except that you don't have to install anything and just launch it within Galaxy, and then it will open a browser window into your web browser, and you'll be able to do pretty much anything that you would do on your local computer directly online. That's where you can use this application. And what's nice is that you can directly use the data that you uploaded within Galaxy in this tool, and then once you did all the different interactive plotting tool for your ocean data, you can get the output of this analysis that you did within ODV back into the history of Galaxy, and then use it into another tool. So for instance, you can use it into another ODV history manager and get the different output into this history here and continue your analysis from one tool to another without having to switch from one different interface to another. And we have also another kind of interactive tool. We have Jupyter Labs. So indeed, from Galaxy, you can directly launch interactive Jupyter Labs. So you'll have the specific environment and the set of notebooks regarding the Jupyter Lab that you wanted to launch. For instance, we have one on Divinity. All of these are also Copernicus data space ecosystem, and so on. You have multiple kind of Jupyter Labs that you can launch within Galaxy. And with that, I think I'm finished, and you can see that the different process of Galaxy is quite easy. You can first discover Galaxy for Earth System Sciences and the different tools it offers. If you see that a tool is missing, you can directly ask for one to be added into Galaxy, or you can add it yourself. It's totally feasible also. Once you have all the tools that you want, you can create your amazing workflow. So you can have a fully automatic one with only batch tool, or you can have one human in the loops. So this is the one where you will have also interactive tool within your workflow. And then once you're happy with your analysis, you can write up an Interoperable tutorial within the Galaxy Training Network. That way anyone can reuse your analysis and easily get a hand on how you did your journey within Galaxy. And with that, thank you very much. And please, if you're interested, go play around in earthsystem.usegalaxy.eu.
Thank you, Maria. I think Massimo is now ready to present. Yes, Massimo, feel free to. Okay, we can see your screen now.
Yes. Okay. I'm unable to start. Okay. Right. Right. Now let's move to the cloud computing platform, which is the analytics engine for large-scale analytical processes behind Blue Cloud. We are a bit on delay, so we'll try to be quick. What is CCP? The acronym for Cloud Computing Platform is a user-friendly data analytics platform that supports method integration, so algorithm integration. The idea is that a scientist can integrate its own analytical process in the platform in any language, and it gets back for free, let's say, a user interface allowing any user to express the input parameters and execute the algorithm, the method, and also the possibility to call the method via web APIs. The APIs supported by CCP are based on the OGC AP processes standard and WPS. And it basically, once a method is imported, it's possible to execute them by any member of the lab, which can in fact repeat and reproduce the execution, share the inputs, the results, and the parameters. In addition to it, it supports the provenance management with the Prov-O ontology. Right, so this is how once you import the method, your script, the algorithm, the software via a Docker container, and you specify the input parameters, you get, this is the let's say the method execution user interface, where you have the list of available methods on the left. When you select one, for instance here we select Ocean Analytics Lab, you as user can of course fill in the inputs required by the methods, and on the right here you see the live execution of the method, comprising the execution logs that are being executed in the Blue Cloud VRE live live, let's say, and then of course you can monitor and get the results. Some nice features that are worth to share. You can share a method link or an execution with your colleagues. So each execution gives you a link. So you can copy the link, paste it to your colleague, and he can or she can repeat the exact execution by just pasting the link in the browser. There is a possibility to embed the methods within Jupyter Hub. So in Jupyter Lab, in different let's say languages, actually there is a code generation tool within the CCP that allows you to get the code to directly embed it in Jupyter, whether in Python or Julia, but also R for those who are keen with RStudio, for instance. Each execution is saved in this file sync and shared service of Blue Cloud that is called Workspace. So every execution is saved. And as I was saying, CCP adopt the Provo ontology, which expresses the Prov data model using the OWL2 web ontology language. So if you hear, sorry, in this example, I'm losing what's happening? Okay. Each execution generate this XML files, which is saved in the workspace as well, where you can see the start and end time of the process, which was the method run, who ran it, and the results and everything else. So how does CCP support open science? It uses digital technologies and collaborative tools. It enables the reproducibility of method execution and the reusability of methods and their outputs. And in doing so, we believe that improves transparencies and ways of disseminating knowledge. And that's it for CCP. Thank you.
Thank you very much, Massimo. And now we have Rainer, who will show us the coastal water dynamics file. Thank you, Rainer. We can see your screen. So the floor is yours.
Okay, welcome everyone. I'm Rainer Schlitzer from the Alfred Wegener Institute in Bremerhaven. I'm reporting in a quick condensed way on one of the pilots of the FAIRIES program, the Coastal Water Dynamics pilot. This is work done collaboratively by Alfred Wegener Institute, colleagues from the University of Liège and also from University of Bologna in Italy.
Apologies, Rainer, we cannot see it in the presentation mode, so if you can switch. Okay, now it's okay, thank you.
Okay, yeah, thanks. So the focus of this pilot is to combine multidisciplinary data sets and by using this combination of diverse data sets, learn more and make better inferences. And we want to use existing software, WebODV, Diva, and DNSource, and extend these to be able to cope and to utilize these multidisciplinary data sets. And just a quick summary, a very wide range of data sets, including marine data, but also river runoff data, meteorological data. These are mostly in situ data. They are complemented by satellite data, and we also include model and reanalysis outputs. And we have chosen as our sandbox, in a way, the Northern Adriatic region, because it's a very dynamic region, and all these processes that I have mentioned, atmosphere, rivers, marine internal processes, they are important to understand important questions. And I've just listed 3 of them here, like biological productivity, evolution of fish stocks, uptake of atmospheric CO2, marine carbon cycle, but also what happens with substances that come with the river. Where are they transported in? Where are they deposited? All these questions, they require multidisciplinary data sets. So the Northern Adriatic is a perfect, basically, sandbox. I will quickly go through achievements, but because we are late, this will be quick. So all these software, they have been integrated in Galaxy, and Marie just spoke about this. There were 2 additional deployments of WebODV on D4Science hardware, but also the Fairies testbed infrastructure. The Liège team, they have produced a new very high resolution climatology in the Northern Adriatic. And here on the right side is an example of that. The source model data comparison software has also been implemented in Galaxy, has been simplified, and here's an example of comparison of observations from moorings and models. Marie also spoke about the data workflows that are installed on Galaxy. This is one example involving ODV, DivaND, and ODV. So coming to WebODV and the servers, these 2 new servers that we have installed focus on satellite data and model and reanalysis data, and they complement the already existing servers up here that have multidisciplinary data from ocean, atmosphere, river, ice, sediment, more than 500 community data sets, including daily updated Argo data sets. So what has been possible all the time is that users open any of these data sets in the web browser, and here in the top row, I've shown just 3 examples open. In addition, users can have the ODV desktop software installed locally on their machine, and they can open any number of instances, for instance, using their private data that they don't want to publish yet. So that has been possible all the time. The new development within Fairies was to link these multidisciplinary data sets by allowing exchange of material from one data window, for instance, this one, to any other one. And this can be between browser tabs, like here, but it can also be between ODV desktop instances and browser tabs. Basically, any data window can act as a donor, but also as a receiver. And what can be exchanged is either graphic elements or data themselves. And I want to quickly show a few examples. And this one is exchanging graphics elements, in this case, the contour lines themselves. So what we are seeing is the color shading is ocean interior salinity coming from a CDataNet dataset here, which clearly shows the impact of the river water coming here from the Po River, affecting the northwestern Adriatic Sea, but also affecting in a narrow band all along the Italian coast. And superimposed on this is chlorophyll A concentration contours from the MODIS Aqua satellite. And what you clearly see is that the impact of the river water indicated by low salinity and the high chlorophyll, they correlate nicely, and people could argue, yes, the nutrients from the Po River, they have an impact on marine productivity. A second example is oxygen profiles in the Eastern Mediterranean here. And the black points are from Argo floats indicated by the blue station points here in this plot. And what you clearly see in the deep ocean, you have these two families of concentration values, and every oceanographer would tell you this is not real. So one of the two is bad quality. And by superimposing the data points, the red points, from a trusted data set, in this case, this is CLODA, located at these red locations in the Eastern Mediterranean, they clearly show who's the real data and who is the problem data. So this is an example where overlay of these graphics elements clearly help quality control. A few examples on exchanging the data and then computing something new, and we will focus on differences. And here is one example that uses the World Ocean Atlas data. And it's focusing on two time periods, 1985 and 2018, and it's exchanging the data values themselves, and it's calculating the difference. How much did temperature change between 85 and 2018? And this is the pattern that comes out, and you would clearly see warming throughout the northern hemisphere, except this famous and mysterious cold blob that has been the subject of many papers. So this is one example. A second example is looking at repeat hydrography. So oceanographers come to repeat selected sections, and this is one here in the Western Atlantic. And they have repeated this now several times, and I'm looking at the difference between 1997 and 21, so almost 25 years difference, and we are looking at dissolved inorganic carbon, and clearly you see big increase where you would expect it near the surface, but even in the deep, you find deliberate signals that have to do with the deep circulation in the ocean. So again, an example of where combining data from different cruises and calculating the difference is very useful. And the final thing that has to do with CFC11, these are these chlorofluorocarbon substances, totally man-made and banned since the 90s through the Montreal Protocol. The oceanographers use them as tracers because it indicates the ocean was free of these substances 100 years ago. If you find them deep down, you know this water has been in contact pretty recently with the atmosphere. And basically for a difference plot between 97 and 21, again 25 years of difference, not a long time. It shows you that basically the entire deep Northwest Atlantic has been impacted by these CFCs. Also, you see a difference near the surface. I leave it as a questions to the audience why this is coming about. So in a quick way, let me summarize. During ferries, we have developed these software, and it's making big improvements. We are allowing a combination of diverse multidisciplinary data sets, and detecting changes becomes easy. And I also want to highlight that most of this development was in close collaboration with Blue Cloud 2026, and we are expecting that the results will benefit the future of Blue Cloud. So with this, I want to thank you with my very quick summary.
Okay. Thank you very much, Rainer, for this presentation. And I believe we reached the conclusion of our webinar today. Just to recap, as you may have understood, we kind of dived into a data management travel. So first we started with data discovery, meaning data needs to be discovered by those who need that. So we need data discovery tools. After being aware we have this data, people need to be able to access the data. So the second part of our presentation, we focus on data access. And before we started with René's presentation, we went to data analysis because we now discover this data, we access the data. Now we need to be able to analyze this in an efficient manner. And the Reina presentation was focused on a joint use case between FAIREASY and Blue Cloud, which had an example how it's important to collaborate together and how it is important, especially to combine different kinds of data in a way that when we combine them, we are able to reach and to achieve more important and content-rich conclusions that will support overall science and also the management of the natural resources. In this case, this is the topic of the webinar. With this, I would like to just invite all our speakers to turn on their cameras. I also invite my colleague Gabriela from FAIREASY communication team. So we would like to thank all the speakers for being here, for sharing your experience and your knowledge, but especially we also like to organize you attendees who had shown interest, who came here to learn directly from our guests and speakers how you can advance data science research and advance overall quality in your daily life. Just an important information. So all the recording of today's webinar will be available on both Blue Cloud and FAIREASY web pages, as well as the presentation from our speakers. And with this, we thank you for your time. We have a slight delay. Thank you for coming and enjoy the rest of the day. Thank you, everyone.